Welcome! To introduce new drone-based technologies into real-world oil and gas operations, you cannot simply slap a new sensor type onto a suitable drone platform and then believe that success will follow. In this presentation, we would like to share with you an approach to operationalize new technologies which we found to be effective to accelerate their adoption. Over the past decade, drones have become an accepted part of the inspection toolkit in upstream and downstream oil and gas for the visual inspection of confined spaces and of tall structures like flares, communication towers and offshore jackets, as well as for the visual surveys of pipelines and construction sites. The benefits of using drones are undisputed: improved safety, lower cost, less disruption, and better inspection information. But yet, most at height and confined space inspection work is still done by putting people in dangerous places. Adding new drone-based capabilities is also still happening at a snail's pace. At the same time, a lot of drone-based developments are underway that could add significant value in oil and gas. We have shown a few examples on this slide. So with all these wonderful possibilities within reach, the real question is, why are these being adopted so slowly in oil and gas? The reason may be found in the contrasting business cultures between the supply side and the demand side. On the one hand, most manufacturers and operators of drone technology are entrepreneurs, many still startups, with no knowledge and experience of the operations, the risk, and best practices in oil and gas. Their entrepreneurial spirit also shows up in their trial and error way of developing and maturing technology. On the other hand, the oil and gas industry is very much focused on risk reduction and therefore highly proceduralized. Even routine activities require detailed risk assessment, check and recheck, and sign-offs. To accept a new technology or a new type of operations may simply have too many unknowns. And when a trial or demo does get approved, too little understanding of the technology's limitations can easily lead to disappointment. To bridge this gap, we propose that both sides agree on a well-defined and step-by-step development cycle that provides the clarity and understanding needed to answer the question, what does it take to accept a new technology for oil and gas operations? This process has to be much more specific than just defining TRL levels. After all, the challenging and high-risk nature of oil and gas operations makes it necessary to integrate crew capabilities, equipment, procedures, and data management as part of this step-by-step development cycle to harden any new drone-based technology if we want to safely deliver consistent, high-value inspection results. In the next section, a practical implementation of such a process is described, using the development of drone-based ultrasonic thickness measurement, or UTM, as a real-world example. In order to operationalize drone-based UTM, we have divided the activities into several work packages that each deliver a defined operational capability, ready to be rolled out in the field. All work packages have the same basic elements, which you can see here for work package A. The starting point is always a dedicated safety case to identify the risks and their mitigation and thus define the necessary training and procedures. In parallel, research, design and hardware integration is done for the payload components that will be used. If the safety case dictates any design changes to the drone or to the new payload, these are also incorporated during this activity. After a green light, the operational procedures and the training curriculum are written and the whole package is flight tested. A final review is done before training and rollout can be started. We will discuss the safety case and the flight testing in more detail in the following slides. Let us now take a closer look at the safety case. For our development program, we have defined 7 steps in line with the requirements from the UK Civil Aviation Authority. We will focus now on the second step, because here we have developed our own very specific approach. Usually, it is a chain of events and not a single event that leads up to a catastrophe. To address this, we have taken an inverse tree approach that starts by identifying the top-level catastrophic events, which you can see in the orange star on the left of the image. We use a broad interpretation of the term catastrophic event that includes any event that, if it happens, will make it impossible to achieve the mission objective because of either safety or performance. So, in our example of drone-based UTM, there can be multiple potential catastrophic events that range from the drone crashing into the structure to failure of the UT probe to obtain a proper reading. For every potential catastrophic event, an analysis is made of all possible causes that can lead up to that event, and then, for each cause, mitigating measures are identified in the form of either a control that reduces the probability of it happening or a barrier that stops the consequence of a hazard after it has occurred. Controls and barriers can be in technical features of the equipment or procedures or training. The risk assessment doesn't stop here. We repeat the same process one level down to find what events or conditions could possibly break these controls or barriers. As a rule of thumb, we want to see at least 3 mitigating measures in any pathway that could lead up to a catastrophic event. If we then take a look at the flight test program that we have followed, we see that comprised 5 progressive phases. The program started with the ground testing. For this, the drone was firmly secured to the ground and all flight and payload functions were tested, also at full drone power. This was done to make sure that there is no mechanical or electromagnetic interference between the drone and payload. After that followed the flight tests, moving incrementally to more operational conditions. We conducted validation flights where the UTM probe was installed but not operated, payload-directed flights in which we took actual thickness measurements, albeit under ideal flight conditions, and mission-directed flights which involved the performance of thickness measurements of real structures under operational conditions. Finally, the documentation flight was used to make sure that all critical elements of the preceding flight test program had been properly recorded, for example on video. Following this approach has indeed brought a number of specific issues to light for which we could put adequate mitigating measures in place. So, we may conclude that a well-defined and incremental development process can provide stakeholders with a much better understanding of a technology's capabilities and limitations, as well as its inherent risks and the necessary safety controls and barriers. We firmly believe that only if all stakeholders agree to use such a systematic way of developing and operationalizing new technologies, we can both ensure the safety, consistency, and quality of drone-based inspections and maximize their value. Without this, the outcomes will be disappointing at best. Thank you for your attention.